Okay, so now we will discuss about the second lateral load resisting system, which is the brace system. We may have three options: X-braced, V-braced and eccentrically braced system. Now, I will unlock the model and I will show you how to put the braces, which are X-braced, and in this case how you can see the model. So 1 second, because I want to delete also on the other direction. Okay, delete. So now I have this frame. Okay, I want X braces. For the X braces, pinned, and let's say this brace, this, and before copying we mentioned that this is a tension only system. Being a tension only system, just one brace will take actual load. We do not consider compression. No. Either delete, let's say, this brace, make a copy of the model and delete this brace, or you can assign for all braces in this direction, assign also in the partial releases, additionally in one part the actual load to be released. Okay, not in both, because you'll have instability, just in one end. It doesn't matter which one. Okay, usually you can release also the torsion. Let's do that. It's not that mandatory because you don't have torsion commonly. Okay, now you can check this here. Okay, it's also P, and here it's not. Okay, so all braces on the left have also axial force reduced. Now I want to select them and I want to copy them here. Okay, no, run the model.
So the brace doesn't need to be pinned also in the X braces.
Yes, good. I will do that just 1 second, because it's for the V brace. Yes. Select HEB. Okay, not like that, but like this. View, 3D view. Okay, no, because you have different section. Okay, and this is A and this should be D. Okay, assign frame releases, and here we want only this. Okay, good. Just wanted to check. So this should be available. It's here, 140 with 8, and I'm very curious of the class, because we discussed about the class. It's something in between, and it's class 1 for S275. Okay, and also for 355 it's also that. Okay, so again, these sections, please make sure, because these are 140 by 140. Okay, please make sure if you choose hollow sections, I will put this to be available. Okay, for round, and make sure that they are class 1. If you use round, it doesn't matter, or square, doesn't matter. Make sure that you use class 1 if you choose ductility class high, 1 and 2 if you choose ductility class H. Now, I want to perform the design, but first let me check dissipative. This should be on Y. Okay. This might be not the most reliable because the ductility, the behavior factor Q, which we reduce from elastic, it's different from X and V. It's I think 2.5 and 4. Okay, but just for the example. Okay. Now, if I pick this and put this, I should also put the combinations with wind, because I'm not sure which is the critical ones. Okay, so you should put all the combinations, perform the checking, and look how we have here. Okay, and here I will display one more thing which is very interesting, is this one. Now, do you see any actual force on this element? 1 kilonewton. That's nothing. Okay, that's how it should be if you want proper design. If you forget to release actual force on one, you'll have tension and compression, which is not correct. Okay, this is mandatory. And now you can assess only this. Let's say this is at 1.6. Okay, and if we go to this, this is greater than critical buckling, force, so on and so forth. It's 670, and we have 1,500. Okay, the problem is that we have NBRD here. So we have 600 divided by 400, which is as expected greater than 1. Question: do we perform stability check for tension on the system? No. How can we prevent that? By introducing, like a cheat as previously, 0.001, 0.01 for buckling length for that elements, because you want just NED over M plastic. Okay, so you either compute by hand and you perform something like this, the section area, yield limit, you need to have the second moment of area, the length of the element, and you have critical force and slenderness. Okay, that should be between 1.3 and 2 for X. Okay, but if you want to have the ratio with sub, you need, for example, let's pick for this, go into overrides, and here you should have that. And in the spreadsheet, okay, here should be tension and slenderness check. Okay, that's all. You don't have compression check. And look, now I have 0.468 because I have 600 divided by 1,500, because it's the same as N plastic, because I don't have stability check. Okay, so actually I'm at more or less 50%. What can I do? Decrease the section, but don't forget not to be in the loop, because when we will check, let's check the displacements. Okay, let's say for serviceability on Y, you're at on Y, yes, 29, less than 30. Okay. Let's put it in millimeters, okay?
It's at the limit.
Look. Okay. So that in a loop. Okay. You can do what? Let's check. This is square. You can go even with circular if you want. Check the properties. But what can I do? Here I have S355. I can go with 275, but take into consideration that I will need to increase the section, because if I decrease the yield limit, I need more area. Okay, so you can play also with this. It's a bit easier to have a lower yield limit for the braces and a higher yield limit for non-dissipative. Take into consideration the overstrength which comes with that, okay, which is higher for S275. But you can do that, okay, and do not forget about the slenderness, okay. If we go to the slenderness, yes, there are a lot of checks, yes. If we go to the slenderness, I have here, just one second. Look, this is uncritical. Okay. But I don't see. Okay. It's not this one. Just one second to check. Because according to this, the slenderness for compression, okay, is this one. Is this okay? Let's check this. This is not reliable because I've changed the buckling length, and for this you'll get 4 millions. But if we go to this, which is relevant because here I have 7.2 meters, which is 1. Mu equal with 1L, okay, because we have double hinge. But N critical, just one second, it should be that. This one, 490 kilonewtons, okay? So, lambda bar, it's actually 1.7. 1.7, it's between this, between 1.3 and 2. You can do that as I showed you here, okay, in an Excel table, because it's much easier. Because you will forget, I didn't change the buckling and so on and so forth, okay? Just one second. Okay, so for X you have this between 1.3 and 2. For V, okay, do not forget that it should be less than 2. Now, it's clear regarding this, and you need to check homogeneity. So if this is on 0.5, I should decrease, but I explained what type of section to take, and you see that I need to check also the stories above to be in that 25%, okay? And after that you can compute omega t, and omega t will be N plastic divided by NED, and you should have the smallest value, or the reverse of the utilization factor, but if you work with non-stability check, because that's what SAP gives you, okay? Now, this is in terms of X braced, okay? In terms of V braced, and I will do it quickly and also for eccentrically braced. Delete. Okay. This it's in D and in, because now I need to put rigid. Assign frame releases this. Okay. In V. Copy from this point to that point, 18 meters. Okay. So for both these, I recommend for centrically braced X and V square hollow section or circular hollow section, which are a bit better. And if you cannot design, just go with HGA section. Now, here they are correct now because we need tension and compression. Okay. Now, when we go here to design, let's say only to this one. And if we check the displacements, we get at 23. So here we can reduce a bit if we need. And we should reduce just for this one. Okay. If I go to this will show me, okay, here in the spreadsheet. So if when you perform this, you need to add also an BRD for buckling, okay? And buckling length for this element, it's for the dissipative, it's 1, okay? Double pin, okay? The simplest one. Now you have NED 600 and NBRD 780, okay? And we have a almost 80%. And if we go to here, you see a buckling length of 5. And if you check in undeformed shape, check here that you have, which is correct, the length is 5. Okay, so this is how you should perform. What's in terms of homogeneity? Just 1 second, and I will reduce also the. Okay, if the element which is the most loaded is 0.05, you can play a bit with utilization factor to have it a bit larger, but let's say 0.7, 0.805 multiplied with 0.25 and delete, you get at about 0.6. okay, this and this should be reduced such that we satisfy the homogeneity criteria. Okay, now this is in terms of that. The displacement should be checked again. Okay, and if we go to the slenderness, we get 1.2 because we have a lower length of the element, which is less than 2. Okay, here don't forget that you need to perform another 2D model to check equilibrium of forces for this. Okay, this I will show you next time. Okay, for the braced system, are there any questions? Is it clear in terms of differences, tension and compression, and what you need to do? Okay. Now, in the last 5 minutes, I will show you the eccentrically braced. Okay, you go here the same, and here you put eccentrically eccentricity, let's say 0.5 meters. Okay, and here should be continuous. Okay, like that. Okay, the thing is that this should be an HEBA something. I don't have here another section. I will pick this to be it as fast as possible, and this element should be divided at intersection. Edit, lines, divide, break at intersection. Okay, and you see that I selected also other elements, because you need to have 3 elements. Okay, you need to have the link different from the beam. 1 second. Okay, so something like that. Why? Because you will change the section of the link. Okay, now I will, before that I need to go to this, delete this, go here, and replicate there. Okay. Okay. Now, you see here that I displayed actual force diagram. Okay. If I will display shear, as expected, I have a lot of stress here. Okay, I have 500 kilonewtons. Okay, and let's check just very quickly a design. And okay, because it increases, and it's according to part 3. If you have here an error, it's more than 50%. Okay, but if you divide, and it shouldn't be 3000. It should be 500. Divided by V CRD. This is not correct. This is something here, a mistake. If this is that, it's 500, not 3000, divided by 1.2, so you get at something like 40-50%. Okay. Just 1 second. Where it's you don't perform the seismic. Okay, the error was that in background it had some checks regarding the seismic code, and I stopped that. You see that I have 0.4. So the error was that according to the seismic code, which I said ignore, yes, ignore special, yes, because we perform the seismic checks, okay, by hand. And now it changed only according to Eurocode 3 and not giving errors regarding some sort of issues. And if you divide 500 by 1200, it's that 0.4. Again, this is HEB 360. You can go to HEA 200, 220, 240, 180. Okay.
The link, right?
Yes, for the links. And then you need to go as much as possible to 100% because you see how easily it is to load them. This I have a very big section, okay? And you need to specify also the homogeneity. Take into consideration here that for the links, okay, for the braces you have the overstrength multiplied 1.1 with omega n factor and 1.25, 35 depending on your steel, okay? And for the eccentrically braced frames, take into consideration that if you short links, you have this, which is as expected. Don't forget that I want you to compute according to this formula, V plastic. You have a different shear area, also the bending moment. Check the length, okay? So you need to have the ratio, the length of the link E less than 1.6 multiplied with this ratio. And for the overstrength, to see at about what value you are. If it's a short link, take into consideration that it's 1.5 multiplied with omega V. Okay, so more or less for X braced, V braced, if you go into annex EF in P100, you should have at least some sort of 2.5, 2.8, something like that for the overstrength. If not, you'll go over Q in sometimes and it's not correct. The design will not be economic. For EBF, you can have even less than 2 if you load them up to 100%. And for the moment resisting frame, depending on PGA, you might be greater than 3, but try to stay between 3 and 4. Okay? Even here, if you check the displacements, and the spectrum, it's not the same, okay, because here the spectrum is the spectrum from CBF, but let's do it because I use the same spectrum. Here I have 3 different projects in 20 minutes what I showed you here, okay? And we started with inverted V. Look, here I have 16 millimeters, okay, compared to 20 something and compared to 29, okay? So assess a bit also that it's also a loop, okay? Okay, now we will start checking the elements in both lateral load resisting systems, but more the elements which are non-dissipative. Now, we will start with the moment resisting frame. Okay, let me check the cases. So we have on X, on Y, and here will be combined. We will discuss regarding the column which is involved structural systems. Okay. Now I want to see the combination. So I have ultimate limit. This is from per system design situation. This is from dissipative on X, and I will also add, I have this, the third one on Y, okay, and this is dissipative, okay, and let's say ULS, this will be 4, but it will be GLS, and I will put it ND from non-dissipative, okay, it will be dead plus life. Again, the discussion regarding snow or not, if you have an open or closed terrace, and I will put the value of the seismic action, but not with 1, with omega t. For the first iteration, you can take the values, then it's on annex E or F, just 1 second, here, okay? You can take omega t 3 for the first iteration, however, please compute the overstrength of the beams, okay? because if you have different seismic action, you might have even 4 and so on and so forth. It's pretty difficult if you have low seismic action and if you consider not a very efficient ductility class. Let's go with 3 in this case. Add, and do not neglect second order effects, so on and so forth. Okay. And now I should choose the design combination. I want from persistent, and I want also from transient, from non-dissipative. We will put also dissipative and check at the base, but let's check from non-dissipative at first. So this is a current frame, yes, it's in axis 2, and these are the values. Okay, 0.85, 0.3, and if I go to the marginal frame, okay, it's 0.6. Now, we haven't discussed anything here regarding buckling length. Okay, if I check, I have from non-dissipative, it's ULS4, okay, it's non-dissipative, and I have a bending moment of 280 on major axis and an actual force of 600. Okay, now if I go to the first one, this is the most stress, and please check the location. Here you see that it's at ground, okay, at 0 meters, here also at 0 meters. There you can check from dissipative. Okay, I have almost double the actual force and almost no bending moment because I did not assign wind load. It's normal this. I don't have wind load on this structure. Okay, and we can check also from flexure. Let's check the buckling length. Okay, it basically took 4 as buckling length, and here it has some buckling factors. Okay, again I suggest sticking to a spreadsheet. Okay, I will provide this in PDF for you, and you should take accordingly the buckling length for base. Please take as hypothesis or very simple 0.7 L for the base and 1 for the current columns. Okay, so if I impose here, let's say for a current one, okay, if I impose here 0.7, you see the values are quite different. Okay, 0.6. Again, this is from non-dissipative, at 0.5 from persistent. Now, I've seen that it's from non-dissipative at base 0.6. If I were to have 0.98, 1.2 from non-dissipative, I can choose to check before that. At 2 meters, for example, we have 0.5. Okay, if it's 0.9 from non-dissipative at 2 meters and 1.2 at 0 meters, you can do this. Put also this one, and check only at 0 meters at ground floor from dissipative. So I have 0.4. So only if you are in the case of amplifying and having huge sections, maybe for this project that's not the case, but you are allowed to do that. Why? Because you allow developing plastic hinges at the base of the moment resisting frame columns. Okay, that's why you can take at the base from dissipative, in other locations from non-dissipative, or in other columns from non-dissipative. Now, any questions regarding the columns from the moment resisting frame? Okay, then I will go to these columns. Okay, make sure I remind yourself. make sure you have the correct orientation. Okay, so here the column should be like that, with the flanges like that for these ones. Okay, the other one should be the other way around. No, let's go back to this. And we should check the, I need another combination, ULS 5, GLS and D. Okay, this is Y. Okay, and here I need to put SY, and I can take from the annex 2. Again, please compute the overstrength accordingly to the utilization factor, or how much the beams or the braces in this case are loaded. Let's take 2. It doesn't matter if it's 2, 2.5, because we have all the structural system. This is just an example for you to understand. And this is for this, and this just to make sure that we have X. Okay. Okay, now I will put it like that. This and this. Now, particularly this frame, it's eccentrically braced frame. Okay. So from non-dissipative combination we should check this, this and this. Yes, these are from non-dissipative. Let's check. Yes, from non-dissipative, from non-dissipative, and from non-dissipative. Okay, and we have a maximum stress utilization factor of 0.6. Okay, at 2 meters, and this is from non-dissipative combination. Now imagine that if you have a plane frame, this would be correct. Why I'm telling you that? If we assess one more time our structure, we see that actually this column is from both. Okay, normally we should have a combined case and check that column. I will do that immediately, but if you want, you can check independently each direction, okay, and do that combined, because in some cases you will get huge sections due to the loadings. Normally this base should be pinned, and then we should have classical independent system on each direction. If it's not the case, we can do like this, and even for all columns. Here we have a loading case in which we combined with one the spectrum, okay, the design spectrum, and we should have a combination in which I will say ULS 6, okay, and I will put G, L, S and D. And here it won't be S, it won't be Y, it will be S, okay, and I will put here with 1. Why? Because I can combine in that loading case after I check the dissipative combination. I can put here the omega t factors, and they will be combined using square root of sum of squares directionally. So you can do that, okay, because you can do this with 3, this with 2, for example, okay, and the combined effect will be taken properly for that column, which is from 2 structural systems. Okay, I will go with okay, yes, and check one more time the combination. Okay, now I need to implement this again for ground floor. you can put 0.7 buckling factors. For others you can have, just 1 second, 1 for all structure. Okay, so you see that from non-dissipative I get 0.2, something like that, and from persistent design situation, only from gravitational loading, I get 0.337. Okay, so actually this is much more demanding in terms of stresses, because it's a combined effect and it's reduced. If you have high stresses, it will be the other way around, because you will get high sections. That's why having an omega T of 4, 5 and 2 and having large spans, you might be in the situation of choosing HEM 600, 700 and so on and so forth, with which might not be the best solutions. But why? Because artificially you may choose, for example, ductility class H where it's not the case. So basically the beams or the links are not loaded, and due to provisions in the code you need to design Q times stronger for elements that are not loaded, which is stupid. Okay, so in order to prevent that, that's why I suggest for lowering PGAs choose ductility class medium according to the current provisions from P100 and Eurocode. Other ductility classes, okay, that are available, but this will help you not to reach huge sections and load on the web the column with 4-5 times the overstrength factor. Okay, that's how you can prevent that. Because if I choose this column and I will check it from this one, maybe it's not the best option. It is from moment resisting frame, but it's on the web, and if I load it in some cases, okay, if I load that column with, this is still correct. If I load it with huge section, that might be the case. Now this is a properly, I think properly designed, at least in some sorts, the example. Indeed, there are second order effects, because if I consider alpha critic I have 7 or something like that, but the section will not be greatly affected. Maybe from HEB 360 might be HEB 400, but it won't be HEM 500, 600. Okay, these are more or less the sections. So that's how you check this. Now, again, if you have the structural system in X, this beam will be designed as a gravitational beam. If you have in V, please don't forget to have a 2D model only of this frame, and check also from force equilibrium, not only from non-dissipative. And this is how you check with sub. Here I did not include the, I did not specify the buckling length. Let's check how much it take. It took 4, but it has some factors here. Okay, so if I specify 0.7, actually the capacity will increase. Okay, you see here that you have also 0.6. And still 1. Okay, any questions regarding modeling, regarding designing non-dissipative elements, at least in terms of checking, obtaining stresses, seeing how we can do it, at least assessing the stresses? I remind one more time, when you do the checking for dissipative, for homogeneity, let's take this frame, okay? And this should be this one. So for shear, you have shear ratios.
Salut, tu voi a te termina.
Yes.
The dissipative element to design close to 1, the ratio.
Yes.
Also.
Yes. Yes. As much as possible close to 1. So
So both non-dissipative and dissipative close to 1.
it's pretty difficult to design, let's say, the columns close to 1. I'll discuss a bit this. But here you check, for example, you see that the links are pretty loaded, okay? From shear force. 1 second. They are pretty loaded in shear, okay? Now, if I were to check this, it's ULS3, okay. Because I have huge sections. If I choose, for example, HE, let's take quickly. HEA 240. I did not check, even the spectrum should be different because this is the spectrum from V, not from EBF, okay. You see I get 1.5. So this is overly stressed, okay. If you check with V plastic from P100, that might be 1.1, 1.2. Nonetheless, you need to have a bigger section. But you see, I get 1.5, 1.59, 1.36, 1. So this should be reduced, okay? Even if I have less than 1, this and this should be greatly reduced compared to the first three, okay? And this is how you have homogeneity. And please play with HA 200, 220, 240, so on and so forth. In some cases, if you go with lower yield limit as 275, this will help you for dissipative, but for non-dissipative, don't forget that you don't have 1.25, you have 1.3, 1.35. Okay, take also that into consideration because omega T will be increased in that case. Okay, now check the homogeneity and then please compute that. Regarding your questions, how much you load the element. Yes, for dissipative, try to load it as much as possible. For moment resisting frame, if you reach from seismic action 0.5, you are the best. Usually it's 0.3 plus minus, that's why you have that 3 omega t, because it's 1 over 0.33. So that's why you get that value. If you get 3.54, you are still okay. Depending on the location, depending on the span, there are several parameters, but roughly that should be the value. For links, as much as possible to 1. For braces, you'll get that limits due to slenderness. If you have X, you can go in actual force, okay, but check the slenderness. For V, you also have compression and tension, so there you need to check also buckling resistance, okay, for the compressed element. There you might not be in the case of reaching 1, because one will be like that, one will be like that, and you should have the same section. You can't have one section in the left, let's say a circumhollow section of 100, and in the right of 200. It's stupid. It's not the case, okay? You should have the same section. That's one thing. Regarding ductility class, please don't forget to check your cross-section class. So if you get with M, you can have section 1 and 2, cross-section class 1 and 2, okay? This is for all dissipative elements, okay? For the columns, basically, or these braces, or this beam, okay, I will put the non-dissipative in this case just to show you again, and put it just on one direction. You see, if I lowered the links, how much the column increased. That might be the case. So in this situation, the best option is to check either like that, a combined effect, and please reassess the overstrength from both directions. Okay. You can put even 0.7, or check from dissipative at base. But this is counterintuitive, because specifically for the brace frame you do not allow plastic hinges at the base, only for the moment resistive frame. So for this one, no. For the others, yes. Okay, so this should be increased in this case, only if putting, let's say, 0.7 here, it did not change, because that K factors of considered also this effect. Please load. A bit, okay? Now, I wouldn't go with 0.95 and 1 for the columns, only if I am forced, but that would be in theoretical cases. Practically, you should think of, okay, what's the case in 10 years if somebody wants to put another story, because the actual force will be loaded, and you have also considerations due to slenderness. Okay, so the column honestly should be 0.678. Okay, even in concrete structures you have that limitations which prevent you from going to that high utilization factors. Okay, also try to assess that even if we do not put another story, maybe the not necessarily the compartment, but you might get different equipment which wasn't considered initially, that will load a lot, even for let's say the system for HVAC. You get some other chillers which are heavier, so on and so forth. So that's why I wouldn't go to one utilization factor for the columns. Okay. For the beams, I told you it's pretty difficult to jump over 0.5. I haven't seen. Okay. From dissipative, because you might get a beam which is from persistent, from gravitational with wind, you can design that at 0.8, 0.9, so on and so forth. Because that's just from one type of loading that you can control. But from seismic, you don't control it. That's the catch, okay? Any other questions?